Consider a solid rod suspended from a rigid support and subjected to tensile force as shown. The stress-strain curve for most materials is a straight line for low values of strain. Hooke's law is obeyed along the straight OA on the stress-strain curve. Accordingly, stress is proportional to strain here, and the slope of the straight line on the stress-strain curve is called modulus of elasticity. More precisely, it is the ratio of stress to strain of an elastic body within its elastic limit. The slope of the straight line OA on the longitudinal stress-longitudinal strain curve is called Young's modulus in honor of the British scientist Thomas Young. Young's modulus is calculated as the ratio of longitudinal stress to longitudinal strain in OA and is denoted by the symbol Y. Longitudinal stress is measured as the ratio of the applied force F to the area A of the face to which force is applied. If the length of the rod L changes by delta L, the longitudinal strain is equal to the ratio of delta L to L. Young's modulus is therefore equal to F by A divided by delta L by L. Young's modulus has the same units as stress because strain does not have any units. Y is measured in newtons per meter square or pascals. Different materials exhibit different values of Young's modulus. The value of Young's modulus for some materials is shown on the screen. Metals generally have large values of Young's modulus compared to other materials. It is a common misconception that rubber is more elastic than a metal, such as steel. This is because you see a rubber band stretching to more than double its length very easily. But steel does not display similar extension. In scientific terms, the higher the Young's modulus of the material, the more elastic it is. This is because a higher Young's modulus means a larger force is required to produce the same amount of deformation in bodies of the same dimensions. The expression for Young's modulus can be rearranged to solve for F, the applied force. If bodies of different materials have the same area of cross-section A and the same original length L, then the material with a higher Young's modulus Y will need a larger force F to be applied to produce the same change in length, delta L. All load-bearing equipment is made or supported by materials such as steel, because they are better able to withstand deforming forces. We will now solve a numerical problem. A load of 40 newtons stretches a wire of radius 1 millimeter and length 2 meters by 0.1 millimeter. Calculate Young's modulus of the material that the wire is made of. The values given in the problem are force F, length L, extension delta L and the radius r of the wire. Since wires have a cylindrical shape, the end face will be circular and the area of cross-section of the wire will be pi times r squared. Now, we substitute all the values in the expression for y and calculate it. Y is 2.5 times 10 to the power 11 newtons per meter square. A 1.5 meter long copper wire is joined at one end to a 2 meter long steel wire of same area of cross section. The combined wire is stretched by a force of 200 newtons. What is the ratio of extension of the copper and steel wires? Young's modulus for copper and steel are 1.1 times 10 to the power 11 and 2.0 times 10 to the power 11 newtons per meter square. The values given in the problem are the original lengths of the two wires, load, and Young modulus for each material. We write the expression for Y for the copper and steel wires. We divide equation 1 by equation 2 and cancel out the equal values of areas of cross-section and the force F. We rearrange the equation to get the ratio of delta L steel to delta L copper. Now, substitute values into the right side of the expression. We simplify to get the ratio of extension of the copper wire to steel wire as 11:15. Young's modulus for a material can be determined experimentally. The apparatus used to do this consists of two wires of the same material of about the same length suspended from a rigid support. At the lower end, the two wires support rectangular frames. The frames themselves support a spirit level between them. From the lower end of one of the frames hangs a fixed load, which keeps the wire taut. This wire is called the reference wire. From the lower end of the other frame hangs a pan that can be used to apply different loads to the wire. This wire is called the experimental wire. The original length of the experimental wire is measured using a meter rule. The radius of the experimental wire is measured at different places using a screw gauge. The area of cross-section of the wire is calculated as the product of pi and square of the average radius of the wire. The frame on the experimental wire has a short main scale, calibrated in millimeters, against which a micrometer screw moves. One end of the spirit level rests on the tip of the micrometer screw. The micrometer screw is moved to make the spirit level horizontal, and the micrometer reading is noted. As a load is added to the pan on the experimental wire, the wire gets extended and the spirit level no longer remains horizontal. The micrometer screw is moved up to make the spirit level horizontal again, and the new reading is noted. The extension of the experimental wire is equal to the distance covered by the micrometer as it moves up. The load is increased by an equal amount, and each time the micrometer is moved up to return to a horizontal position and the reading noted. The difference between the reading with the load and without the load is used to calculate the extension caused by that load. A graph between extension and load is plotted. It is a straight line for low values of strain. Young's modulus is calculated using the expression for y. The ratio of force F to extension delta L is calculated from the extension load graph, and the values of L and A are substituted. In this experimental method, tensile forces were used to determine Young's modulus. Similar results are obtained even if the load causes compressive stress by using a suitable experimental setup. We learned that Young's modulus can be experimentally determined by applying different tensile or compressive loads and measuring the change in length in each case. Consider a cubical body as shown. When a pair of equal and opposite forces is applied tangentially to opposite end faces of the body, the shape of the body is distorted and the stress generated is called tangential stress or shear stress. Shear stress is measured as the ratio of applied tangential force F to the area of the face A. When a tangential force is applied to the top surface of the body, the top surface is displaced laterally with respect to the bottom surface by a small length dx, and the edge perpendicular to these two faces rotates through a small angle gamma. Shear strain is defined as the ratio of the lateral displacement of the top layer of the solid with respect to its bottom layer, which is the ratio dx to h. This is equal to the tangent of the angle gamma, where gamma is expressed in radians. If the value of gamma is very small, tan of gamma can be approximated to gamma, and hence the value of gamma is calculated by taking the ratio of dx to h. The ratio of shear stress to shear strain for a material is the shear modulus or the modulus of rigidity and is denoted by the symbol G. Shear modulus has units of newtons per meter square or Pascal. The values of shear modulus for a few materials are shown. Most materials have shear modulus values lower than their Young's modulus, and typically about 1/3 of their Young's modulus value. We will now solve a numerical problem. A cubical block of steel of edge 10 cm is held fixed at the bottom face, and a tangential force of 10 to the power 5 newtons is applied to the top face. Calculate the shear stress and shear strain. The modulus of rigidity of steel is 84 times 10 to the power 9 newtons per meter square. The values given in the problem are the tangential force, the edge of the cube, and the modulus of rigidity. We calculate the area A of the face to which the tangential force is applied. Each face of the cube is a square, so the area would be equal to the length of the edge squared. We express the length of the edge in the SI unit, meters, before calculating A, and A is 10 to the power minus 2 meters squared. Shear stress is the ratio of the tangential force F to area A. Substituting the values of F and A, we get shear stress to be 10 to the power 7 newtons per meter square. The modulus of rigidity is the ratio of shear stress to shear strain. Arranging the relation to solve for shear strain and substituting the value of G and shear stress calculated earlier, we get shear strain as 1.19 times 10 to the power minus 4. Remember, strain has no units. We will now learn about bulk modulus. When deforming forces are applied perpendicular to a body's surface at each point, the volume of a body decreases and the stress generated is called bulk stress or volume stress. Forces acting perpendicularly inward at each point on the surface of a body are equivalent to a uniform increase in external pressure. Therefore, bulk stress is defined as a change in pressure delta P, which is also equal to the ratio of force F to area A. If the volume of a body V changes by delta V, then the bulk strain or volume strain is equal to the ratio of delta V to V. The ratio of bulk stress to bulk strain is called bulk modulus and is denoted by the symbol B. Bulk modulus is equal to the ratio of delta P to delta V by V. An increase in pressure causes a decrease in volume, which means that a positive value of delta P causes a negative value of delta V. Therefore, the expression has a negative sign to give a positive result for B. Bulk modulus is measured in units of newtons per meter square or pascals. The reciprocal of bulk modulus is called compressibility and is denoted by K. The values of bulk modulus for a few materials are shown. Data shows that solids have the highest values of bulk modulus, followed by liquids and then gases. Gases have an extremely small bulk modulus. As compressibility is the reciprocal of bulk modulus, this means that gases have very large compressibility compared to liquids, and liquids have higher compressibility than solids. The compressibility and bulk modulus of gases depend on the pressure and temperature of the gas. The reason for the huge difference between compressibility of gases, liquids, and solids lies in the intermolecular forces of interaction in the three states of matter. The molecules of a gas are so far apart that there is a negligible interaction force between them. liquids have a strong intermolecular force of interaction, whereas solids have the strongest interaction between their molecules. We will solve a numerical problem. A cubical block of steel has an edge of 10 cm when subjected to a pressure of 10 to the power 5 Pascal. What is the change in its volume when the pressure on it increases to 26 times 10 to the power 5 Pascal? The bulk modulus of steel is 160 times 10 to the power 9 Pascal. The values given in the problem are the length of the edge of the cube, the original and new pressures, and the bulk modulus of steel. The original volume of the cube is cube of the edge. Expressed in meters, the original volume is 10 to the power minus 3 meters cubed. The bulk stress, delta P, is equal to the change in pressure, and substituting the original and new pressures, delta P is 25 times 10 to the power 5 Pascal. Bulk modulus is the ratio of bulk stress to bulk strain. We rearrange this expression to solve for delta V, the change in volume. Substituting the values of delta P, V, and B, we get the change in volume. Delta V as minus 1.56 times 10 to the power minus 8 meters cubed. The negative sign in the answer means the final volume is smaller than the original volume. Man has made structures such as skyscrapers and overbridges to make life convenient. Such constructions must be designed for safety. Otherwise, there could be disastrous consequences. The design of safe and appropriate structures involves choosing the appropriate material in appropriate shapes and size. Let's take the example of a crane used to lift heavy loads. The highest value of stress the crane's rope can be subjected to must be lower than the breaking stress value of its material. Consider a crane designed to lift loads of up to 1 ton. With the rope made of steel, of breaking stress 400 times 10 to the power 6 newtons per meter square. The cross-sectional area of the rope can be calculated by equating the breaking stress SU to the ratio of maximum load and the area of cross-section A. The cross-sectional area of the required rope is calculated for the maximum load of 1 ton. That is 1000 kilos. By substituting the maximum load as mass times acceleration due to gravity and the breaking stress. The required area is 2.45 times 10 to the power minus 5 meters square. As the cross-section of the rope is circular, which is equal to pi r square, substituting and simplifying for the radius, we get the radius of the rope as 2.79 millimeters. In practice, a large margin of safety is provided and thus a thicker rope, say of about 8 millimeters, is recommended. It is also found that a collection of thinner wire strands, when compacted together, make the rope stronger than a solid rope of the same cross-section. That is why crane ropes are made of several strands instead of one. Structures such as bridges and tall buildings that have to support static or dynamic loads are generally constructed using pillars and beams to support them. The beams used in buildings and bridges have to be carefully designed so that they do not bend excessively and break under the stress of the load on them. Let us consider a beam resting at both ends, subjected to a load W at its midpoint. The beam has a length L, width B, and thickness A. When a load is exerted at its midpoint, it bends as shown. In the process, the upper surface is compressed, whereas the lower surface is extended. The beam will sag or deflect due to the load. The deflection of the beam at the midpoint is its vertical deflection compared to its unstretched position. The greater the width B of the beam, the greater the maximum load of the beam can support. The deflection delta at the midpoint can be determined experimentally as well as theoretically calculated. As the calculation involves high-level mathematics, we avoid the derivation of the expression in our context. It is equal to the load W times the length L cubed divided by 4 times the product of the thickness A, width B cubed, and Y, Young's modulus of the material of the beam. It must be kept in mind that the beam bends less for a given load if the width B is greater and the length is smaller. This is due to the fact that the deflection of the beam due to the load is inversely proportional to the cube of the width and directly proportional to the cube of the length of the beam. Also, as the deflection of the beam is inversely proportional to just the single power of the thickness of the beam compared to the cube of width, the thickness of the beam does not have as great an effect on the maximum load that can be supported as the width. But on increasing the width B, unless the load is placed at the right place, there is every chance that the beam will bend as shown. Such bending is called buckling. Thus, the beam can buckle under asymmetric loading, which is the case in bridges that carry differently distributed traffic at different times. To avoid this, the cross-section of the beam is chosen to be an I-shaped, as shown. This shape provides a large load-bearing surface and enough depth to prevent bending. It also reduces the weight of the beam without compromising on its strength to bear loads. The pillars used in buildings and bridges are also modified to be able to support greater loads by making the ends distributed. The elastic properties of rocks can help calculate the maximum height of mountains on the earth. At the bottom of a stable mountain of height h, the stress must be less than or equal to the elastic limit of the rocks, even though there is no uniform distribution of the weight of the mountain on the rocks at the bottom. The stress due to the weight of the mountain at its base will be equal to h rho g, where rho is the density of the mountain rock and g is acceleration due to gravity. The stress due to the mountain's weight can be equated with the yield stress, the stress at the elastic limit. The value of yield stress for rocks is typically in the range of 3 times 10 to the power 8 Pascal. Taking an average density of rocks as about 3000 kg per meter cubed and solving for h, we get h as approximately 10 kilometers.